On the board, you can see 9 problems about tensor calculus. The first one, if A is a second-order constant tensor, it means that all components are constants. In three-dimensional space, compute the divergence of the product of this matrix and X and X. From the definitions, you know that this expression in the divergence is a second-order tensor, since the dyadic product of two vectors is a second-order tensor or a matrix, and the dot product of two matrices is again a matrix. So the divergence of we have a divergence of its second-order tensor, so the result is a vector. Let's translate this expression to the tensor notation. This will help us to manipulate the mathematical relation easily, manipulate them and find the result in two lines. Okay, let's start from the core of the expression. Here I have selected I and j as indices of this matrix. So A sub ij, this is a vector, so I need one index here because we have a dot product here. So this is the contracted product. So the index of x should be identical to the second index of the matrix. And finally, I have another vector. So x sub k is the last term in this relation. This is the divergence. Divergence is the contracted form of gradient. So I need the partial derivative with respect to x here. But the index k and here the index of x should be identical again because this is the divergence, or the dot product of the del operator and this tensor here. The rest of the proof is so straightforward. A sub ij is a constant matrix, so here I can put aj at the beginning, and also I have two vectors in the derivative, so I can expand this relation using the rules of derivation of product of two functions. So I have a sub ij, x sub j times a partial derivative of x sub k with respect to xk, but both indices are k, and plus a sub ij, x sub k times the partial derivative of x sub j with respect to xk. As you know, the derivative of x with respect to x is the identity matrix, or the Kronecker delta. Here x sub j, the derivative of x sub j with respect to x sub k is delta Kronecker sub jk. And here it is the contracted form because both indices are k. So this derivative is delta Kronecker sub kk. Again, as you know from the simplest form of tensor identities, delta sub kk equals 3. And so this is 3 times x sub j, a sub ij. And this one, as you know from the rules of tensor notation, that the Kronecker delta is the substitution tensor. So here I have a k here in the as the index of x, and I have another k here. So j, you can replace k by j. So the result is a sub aij x j. So I have two similar expressions, and the result is 4 times a sub ij times x sub j. The second question, if c sub ij equals c sub ji, it means that c is a second order symmetric tensor, and also is a constant tensor. It means that the components are all constants. Find the result of this expression. As you see, this is directly written in tensor notation. C sub ij xi, xj, all. You see a comma in the index. It means the derivative with respect to x sub k. This is the short form of this expression. So the difference between this expression and the previous one is that this is the divergence, and I have an identical index. But here, this, as you see, the derivative is with respect to x sub k. Okay, so again, I can expand this derivative using the rule of derivative of two functions, product of two functions. C sub ij is a constant tensor, so C sub ij, xj, the partial derivative of the next one, and C ij, xi, the partial derivative of the previous one, x sub j. The rest of the proof is similar to the previous one. This derivative is x sub I with respect to x sub k, so the result is delta sub ik. And this one is delta sub jk. And I can see another I here, and this is delta ik. So I have to replace k here. And similarly, I have delta jk, and this is cij. So this one should be c sub ik. This is the result, c sub kj, x sub j plus c sub ik, x sub I. And since the tensor is symmetric, it means that I can change I can flip its indices. So this is c, for example, c sub ki xi. And since I and j are both dummy variables, so you can replace I with j, and the final result is twice c sub kj, x sub j, which is again a vector. Here I have c sub ij, xi, xj. So I and j here are dummy variables. So the result of the expression in bracket is a scalar, and this is the gradient of a scalar quantity, which is a vector. The third question: what is the determinant of the dyadic product of two vectors? For example, a and b. This is the dyadic product, or sometimes you can omit this strange symbol here and simply write a, b near each other. The determinant of the dyadic product of two vectors. What is the result? Let's again translate this expression to the tensor language. Then we can easily manipulate this relation and find the result. Okay, suppose that, as you know, the dyadic product of two vectors is a second order tensor, a matrix. Let's show this matrix by x sub ij. And this is the definition of the determinant in tensor notation. This is the permutation symbol. Epsilon sub ijk. X is the dyadic product of a and b. X sub 1i, x sub 2j, x sub 3k. This is the definition of the determinant of the matrix X. Now replace the matrix X, the X equals A sub I times B sub J. So X sub 1i equals A sub 1 B sub I. X sub 2j equals A sub 2 B sub J. And similarly, X sub 3k equals A sub 3 B sub k. These are common product of scalars, so you can change the sequence of multiplication. So I have written 3a, a sub 1, a sub 2, and a3 near each other in a bracket, and also b sub I, b sub j, and b sub k in the second bracket. These are constants, but as you see here, I have an anti-symmetric tensor, which is the permutation symbol. And this bracket, this term here is asymmetric. third order tensor, because if I change the index of this third order tensor, for example, I and j, these are simple multiplications, so the result is does not change. So this third order tensor is symmetric with respect to I and j, and also with respect to I and k, and also with respect to j and k. And also we have at least two identical indices between the permutation symbol and also this third order tensor. You see I, j, k, and again I, j, k. And you know that the double dot product, double contracted product, and also the triple dot product of F, an antisymmetric tensor, and a symmetric tensor equals 0. So the determinant of the dyadic product of two vectors is 0. Question number 4. Consider this relation. T sub ij is a second order tensor equals S sub ij plus 3 times S sub kk, or the contracted form of the tensor S or its trace, times delta sub im times delta sub jm. As you know, the product of these two deltas is delta sub ij, because m is similar between indices, and you can omit m and simply write the result of this multiplication, delta sub ij. This is the first step. But find this question mark here. I want to compute s sub ij, which is equal to t sub ij minus an unknown coefficient, and t sub kk times delta sub ij. As you see, these expressions are totally identical. There is only one difference between them, which is s sub kk. Here I have t sub kk. So I have this relation, and I have to compute s sub kk as a function of t sub kk, to replace in the first one and find that unknown question mark. So using the first relation, I can multiply both sides by delta sub ij, or I can contract both sides of the relation. So the contracted form of this tensor is t sub ii. The contracted form of s sub ij is s sub ii. And also, this is a scalar. 3 also is a scalar. And the delta sub I, the contracted form of the delta ij is delta sub ii. And as you know, again, this quantity equals 3. I have another 3 here, so this is 9. And 9 plus 1 is 10. So t sub ii equals 10 times s sub ii. So replace this relation here. S sub ii is 1 over 10 times t sub ii, 1/10 of t sub ii. So s sub kk, which is equal to s sub ii, because I is a dummy variable, is a dummy index. So s sub ij equals t sub ij minus 3 over 10 t sub kk delta ij. The fifth question: if t sub ij is the second order tensor and equals x sub I times x sub j, it means that the t sub ij is the dyadic product of the x vector and the x vector. X, dyadic product x. Then find the partial derivative of t sub ij with respect to xk times delta sub ij. What is the result of this tensor expression? Okay, as you know, if I multiply the Kronecker delta, I should find, for example, I here and replace it with j, or replace j with I, no difference. So the result of this product is simply the partial derivative of t sub I, and with respect to x sub k. Now replace the contracted form of t sub ij from the first relation. Multiply both sides by the Kronecker delta sub ij, and t sub ii equals xi times xi again. So tii equals the partial derivative xi, and with respect to x sub k. Pay attention that you cannot write xi times xi something like x sub I squared, because we have to keep two identical indices in the relation that help us to apply the Einstein's convention, summation convention. Okay, then it's so easy. The rest of the problem is so straightforward. This is again the rule of derivation of a product of two functions. So the first, the derivative of the first times the second, and the derivative of the second times the first. So twice x sub I, the partial derivative of x sub I with respect to x sub k. And this is again the Kronecker delta Kronecker's delta sub ki, and we have I here, so this is the product of x sub I and delta sub ki is simply xk twice x sub k. The next question, this is a second order tensor or a matrix, a symmetric matrix, as you see, 6xx, x84, x4, 9. And it's known that the product of eigenvalues of this matrix is 120. So what is x? The magnitude of x, the value of x. As you know, the determinant of a matrix is the third principal invariant of that matrix, and also the determinant equals the product of three eigenvalues of the matrix. So this number here equals the product of the eigenvalues and also equals the determinant of this matrix. So you have to simply compute the determinant with respect to the first row. So 6 times 72 minus 16 plus the second column x times 4 times x minus 9 times x plus x, and the determinant of this sub-matrix here. And you have to solve the quadratic equation, and the roots are positive, negative, root square of 24. The next question, what is the result of integral of x sub I times n sub j ds? And S is a closed surface surrounding a volume, and n is the normal outward unit vector of that surface. What is the result of this integral? As you see here, I have the dyadic product of two vectors. The first one is x, and the next one is the normal unit outward vector. This is equal to the dyadic product of the del operator and this vector here, x. So I have to compute the dyadic product of the del operator and x in tensor notation. This equals the partial derivative of x sub I with respect to x sub j, which is again equal to delta sub ij, which is a constant tensor, and the integral of dv is simply v. So the result is the product of delta sub ij and v. Next question, compute the volume integral of the permutation symbol here, epsilon sub pqi, times a vector c sub I dv. And the vector c equals, again, another permutation symbol, epsilon sub I jk, times a second order tensor a sub jk. As you see, j and k are dummy variables, so the c's should be a vector. So this is a vector here. Then simply replace this expression here and to the product of two permutation symbols with one identical index appears in the relation. And use this, so I have to compute the volume integral of epsilon sub pqi times epsilon sub jki times a sub jk dv. And use the very important and very famous tensor identity, which expands or decomposes the product of two permutation symbols with one identical index, like this. So this is the relation between the Kronecker delta and the permutation symbol. And this is again the rest of the expression is exactly similar to the previous one, and then start to multiply these deltas by that tensor one by one, and use the substitution property of this Kronecker delta, and you can finally find this expression. Now use another information that the matrix A, or the second order tensor A, is an anti-symmetric constant tensor. Since A is anti-symmetric, so if you flip the indices, a negative sign appears in the relation. So A sub QP equals negative of A sub PQ. So you can change the order of indices and replace this negative sign here by a positive sign. So, and also A is a constant tensor, so the result of this expression is twice A sub PQ V. V is the volume. The next question, find the result of this surface integration. Closed surface. S is the closed surface bounding a volume in space. And this is the permutation symbol, epsilon sub ijk times f sub k times n sub j and ds. Here, as you see, we have an identical index and also another identical index here. So this tensor expression equals the dot product of n, which is the outward normal vector of the closed surface S, and the dot product of n as a vector, and this expression. So based on the divergence integral theorem, the surface integral of the flux of a quantity, here our quantity is this one, equals the volume integral of the divergence of that quantity integrated inside that volume. So this one equals the divergence of, this is our quantity integrated over the volume inside that closed surface. Okay, the divergence is the derivative with respect to xi, and I should be identical with the first index of epsilon, so because this is the divergence, not gradient, and the rest of indices are exactly similar to the previous one. Epsilon is a constant tensor, so and the partial derivative with respect to x sub I appears here. So here I have the gradient of f sub k, or partial derivative of f sub k with respect to x sub I. Let's play with indices here. As you know, in tensor notation, I can replace a non-repeating index in all terms in the relation with another index. For example, I like p, someone else likes l. So in this relation, I have j and k, and I can easily replace k with j and j with k. So anywhere in this relation, when you find, for example, j, you have to write k instead, and when you find k, you have to replace it with j. So epsilon sub ijk will be epsilon sub ikj. And also here, the partial derivative of f sub k should be the partial derivative of f sub j with respect to x sub I, and I is the same. So, and similarly, let's continue the game. I can replace the all i's in this relation with k and all k's with I. So epsilon sub ikj will be epsilon sub kij, and in the integrand, the partial derivative of f sub j will be, with respect to x sub I, will be the partial derivative of f sub j with respect to x sub k. And again, as you know, the permutation symbol k sub ij is exactly equal to the permutation symbol epsilon sub ijk. And this is the final result. Epsilon sub ijk integral of fj, partial derivative of f sub j with respect to xk dv.